example where we looked at the single state, and this state was not an eigenstate of the system, and we tried to understand what would be the effect if the state is in the continuum or is coupled to the continuum. And there were two things that we learned from that exercise is, one, that virtual excitation into the continuum can give you a real correction. So if I had a state, so I had my potential, and then there was a state here. So even if the state is bound, and this is the continuum, then virtual excitation into the continuum and then back changed the energy of that state. So I had, as a function of energy, so I had term delta of energy, which was just due to these virtual excitations, and then minus IW energy over 2, which is the imaginary term, and this term only appears if the state, so this term only appears if your energy is above energy threshold. Of course, in our example, that was 0. Okay, so we had this exercise, we went through it, and we obtained this result from the perturbation theory. So this was an example of the perturbation theory. So now let me take a formal approach and discuss with you generally what's called a Feshbach projection formalism. Well, last time, of course, I called it gamma because this is just a single number. Yes, so I use W right now, thinking more generally already, because this is, in that example, this is just the energy. So this is a number, right? So you just, a perturbation theory, you add energy to your state. Okay, but in the more general formalism, this is not going to be just energy. This is going to be an operator. So if you have many states, and this is where I'm leading you to. So in this example, this was just gamma of, or capital gamma, use the small gamma and the capital gamma. So was simply equal in this case to this W of energy, and it was also equal to 2 pi, and then here we had an overlap between my wave function, my potential, and my state in the continuum in the energy representation squared. So then I don't need to have any extra factors. Okay, so this was that example. So now I would like to discuss this Feshbach projection formalism. So the idea of the projection formalism is as follows. So let us think of some states which are bound, like this one. And I can make many of these states, or maybe my system has many of these states. And again, later on when you discuss many-body physics, then there is a well-known nuclear shell model approach. So in the shell model, all states are considered to be bound in the harmonic oscillator potential, as an example. Then naturally, this space of bound states would be a separate space from the continuum. So let me say that there is a space P. So a space, in this case, I will think of it as a space of bound. And I call this space P, and also I think of P as being an operator that can project into that space for convenience. So if it is a projector, then P squared equals to P in terms of an operator. So projecting twice is equivalent to projecting once. Okay, so and then there is a remaining space Q, which is the space of continuum. states. So far, I don't even have to make these distinctions. I'm just going to call again another projector Q equals to Q squared equals to Q itself. So these are just projectors, and I can think of in terms of a projector P plus Q being unity, right? So then it's a complete projection. Okay, so this is an example. Then, of course, if I have my Hamiltonian, then Hamiltonian has multiple components. So my H in general can be written as H, which takes me from P to P, which is the part inside. Then there is obviously H for Q. And then there is two parts which are obviously separately non-Hermitian, PQ plus HQP. So this takes me from space Q component and brings me to P component, and this is vice versa, right? So this is just a general Hamiltonian split into sections. And you can think of it as just being a matrix, right? So if I were to think of a matrix, then this is just, let's say here I would have H, P, P. Here I would have H, Q. Q is sort of like a block matrix. And this is H, P, Q, and then H, Q, P. Right, so it's like a block matrix. All right, so then I can write my Schrödinger equation. And the Schrödinger equation I can write in terms of components. So first of all, if I think of a full Schrödinger equation in the P space, then I would have HPP acting on my psi plus HPQ acting on my psi, right? So far, the end result of this action is always in the P, right? So this takes me from P, brings me to P. This takes me from Q, brings me to P, right? And then there's no other components, and this equals to energy multiplied by P projected into the psi, which is my wave function. So this is a P part of my Schrödinger equation. Then I have the same for Q part, so which I have HQQ psi plus HQP psi equals to EQ psi. So this is now a part of the Schrödinger equation that lives in the Q space. Of course, they're coupled. I mean, this is just the same as if I take this matrix and multiply it by P psi Q psi, I'll get that combination of equations, right? So this is a 2 by 2. You can think of it as a block equation. All right, so then the projection formalism works as follows. So let me consider my equation, and let me take a look at this term. So in this term, what I will have here is what I can extract is H Q P psi equals to E minus H. So if I move this to the side, E H Q Q multiplied by the Q component of the psi. So therefore, my Q component times psi can be written if I act with the inverse of this operator, so which is going to be 1 over E minus QQ times H Q P psi. So this is just an algebraic manipulation. So what I extracted is this component now, which is a Q portion of the wave function. Okay, so now I have a Q portion of the wave function, and this is what I'm missing in this equation. So in this equation, this HPQ takes a Q component of my wave function and acts on it. So therefore, I can combine this and write, so this was obtained from the second equation. Now I'm going to take the first equation here and write it in the following way, that HPP acting on my wave function psi, then plus in this term is I'm going to replace, right? So this is HPQ. So of course I'm free to put Q in here because this takes me from Q space and puts it to P space. So it only works on the Q part. So putting another Q is not going to change anything, right? So, and instead of this QP, I'm going to put Q psi, I'm going to put this function. So therefore I have HPQ, which is this one, acting on this Q psi, which I'm going to take from here. So this is 1 over E minus HQQ multiplied by HQP psi. And this equals to this E times P psi. Okay, so this is my final equation that I obtained, and the nice part is this equation is the equation for exclusively for a P space, right? So I'm free to put everywhere P psi if I wanted to, right? Because this is just not going to change anything because I have always P acting on the component. So this is an equation for a P space evolution. It is an exact equation. Nothing has changed. And what I can do now is I can actually relate it to my earlier problem of one state and see that effectively I can say that inside of my P space, where I have my many-body space, if I restrict my consideration, I can still obtain an exact Schrödinger equation which has this H of E, which has energy dependent, and this H of E, my Hamiltonian, is, or acting on psi, let me put it, is going to be the following. It's going to be my original H, which is constant times P component, and then plus this extra term, which H PQ 1 over E minus HQQ HQP times psi. So this is my sort of effective Hamiltonian, and with effective Hamiltonian I can associate these parts. So let us now more specifically think of a wave function as being these two components. So I can say for inside I have sum of some coefficients alpha 1, basis states 1. So these numbers 1 correspond to some basis state 1. Alpha is just a coefficient. So if I had just bound states, this would be my space. And this is a summation over all possible basis states 1. So this part is in the P space. Then I can imagine having some continuum states, which now has a summation over a discrete channel space, which we discussed before. There are various channels, and their number is discrete, again for one body case, so channel. And then, of course, it's a summation over all energies, which I have to write as an integral. And then there is alpha, which is a running constant, which depends on the channel and energy E for that particular state. And now this is my continuum state, basis state, which is labeled by a channel and the running energy E. So as before, in our simplest examples, I was using, in one body case, I was using state's energy like that, right? But this was one particular state for one particular particle, let's say proton or neutron. Now I may have many channels. So for each one of those, I have to have this. Moreover, the channels now can be generalized because I don't have to have a simple particle like a proton. I can have a more complicated particle which may be a whole nucleus or a whole cluster, and the whole cluster can be in a number of intrinsic states. So this refers again to the channels we discussed in the simple model of reflection from an infinite wall, where each channel was a different state and the harmonic oscillator potential. So now I have this whole picture. Okay, so then my equation of interest that I will get here is, or my effective Hamiltonian, can be written as a matrix in bases 1, 2, because it completely lives in the p space. So then I would have this H matrix element 1, 2 is going to be my original 1 Hamiltonian 2. Then this part is plus, and here I will have the following. So here I will have I can insert a summation over all complete set. So in here and in here of these continuum states. So assuming, let me write this somewhere. Maybe I can erase this and write that, of course, I have a completeness for a P projector or Q projector is effectively sum over all channels integral over all energies dE. And then here I have CE, right? That is a complete projector on this space Q. It's just a summation and integration of all possible cases. So I can insert this twice in here because this is my Q space. So this stuff here takes part in the Q space. So therefore I will write it as sum over C for this one, and then there would be another one here, so I'll put C prime here. And then I have two integrals over dE and the same dE prime. Well, actually, let me put prime and double prime here, and I'm going to do the same, C prime and C double prime, because I have running energy E, which is here, so I don't want to confuse another E. Okay, so then I will have this expression twice. So I will have here my original state 1, which is here, overlapping this P, Q. And then I have here first index, which is with primed. So I have C prime, E prime. Then I will close it, again C prime, E prime. And then here I have my over E minus H Q Q. Should probably erase some more to clear up space here for you to see better this expression. And then I have another projector on the other side, so this is prime, C double prime, E double prime, and then here C double prime, E double prime, H Q P state 2. Right, so this is the same expression, just I took an overlap between 1 and 2. So this is my definition for effective Hamiltonian. And of course, this effective Hamiltonian also depends on the energy E, which is here. Right, so we already noticed one important thing about the Feshbach formalism, that by doing this trick, what I have done is I call this whole thing as an effective Hamiltonian. But this effective Hamiltonian has energy here. So my eigenvalue problem has the same energy on the other side. So in fact, I'm not cheating, because previously I had a linear problem, which was a diagonalization in the full space. Now I have simply a non-linear problem, which has energy, and I have to solve it iteratively in some way. I have to make sure I end up self-consistently. Now, if you're worried about mathematics, you also know, for example, that if you're diagonalizing a matrix, okay, one option is to do a linear transformation, linear rotations, to bring it to a diagonal form. Another option is you write down an eigenpolynomial, which is a pi order polynomial, and you solve it. So the second option, you just get one equation, but it's a nonlinear equation that you have to solve. So you can see that there's no tricks here in the sense of mathematics, that you still have the same problem to solve. All right, so now let's talk a little bit about this equation. So in this equation, the common assumption is that I can diagonalize this HQQ, that actually these states C are diagonal for HQQ. So, which is a natural assumption that far away in the continuum, I do know how to solve my scattering states, which, remember, we started our course by saying I have to separate some H naught, which defines me what happens far away. So what happens far away determines this HQQ. And typically that's just a kinetic energy, and in addition to that, if you're discussing cluster, that would be an eigenstate. So again, referring to our problem of two particles bound by harmonic oscillator scattering over well, far away, we know the Hamiltonian and we know the eigenstates, that the eigenstate is a product of translational motion with some momentum times the intrinsic wave function, which is an eigenstate of a harmonic oscillator. So that would be your channel, and we know that. So therefore, I would assume that HQQ times CE is diagonal. Let me put prime here. So it just gives me E prime times the same thing. Right? So therefore, if it's diagonal, then this goes through completely, and I will simplify my H12. So this is my curly H12 energy. So one simplification is that, of course, instead of operator, I will put just energy prime here, because then it's diagonal. Second simplification, that this overlap between C double prime, so between these states, gives me a delta function, which I can write explicitly. So C prime E prime, C double prime, E double prime gives me a delta function of C prime, delta function of running energy. Right, so this is a normalization condition for these states. Also, let me now call this, just define a simplified notation and call this an amplitude. So this is amplitude, which is a function of energy prime that refers to channel C here and the state 1, just as a definition. So then, to shorten notation, basically. So then this is going to be my original Hamiltonian 1H2, and then I will have plus here summation over O channel C prime, integration over D E prime. This is my channel A, or the amplitude A. This is my energy, so I have A C1 of E prime times 1 over, and this is now a number, E minus E prime, and multiplied by this amplitude, which is A of C2 E prime, and of course this is complex conjugate, so this is just star. Okay, so what I did is clearly one integration here. I had two integrals here. I can write it just to be sure that there were two integrals. One integral and one summation disappeared because of orthogonality. So then labeling these as amplitudes, I will get this expression. Okay, so this is a complete formalism. There are some statements that I can add here. What I also assume is that spaces are orthogonal. So all states, in fact, these two state 1 and the continuum state are orthogonal to each other, so their overlap is 0. That is the assumption that I presented here, although that assumption can be lifted. So it's not necessary to have that assumption. It's somewhat more complicated derivation, but it can be easily removed. Okay, so this is my now effective Hamiltonian. And as before, this effective Hamiltonian, I can address this integral over the continuum using real and imaginary parts. And if you look and compare this with my previous one particle in the well problem, this is actually exactly the same. So it's exactly the same, except now we know this is an exact solution or exact equation. So what I can write is that my H effective Hamiltonian is energy dependent here between 1, 2. And then it equals to my original Hamiltonian between the intrinsic states 1 and 2. And then I can have plus a principal value, and the principal value is just this integral, right? So I will have delta 1, 2, which depends on energy. Okay. So, and as before here, I will add plus I0 to assure correct correct signs of imaginary parts. So this is now the principal value is the delta. So delta, by definition, 1, 2 is just going to be an integral of A, C. So it's a summation over all channels, an integral over all energies, E prime, A, C, 1, 2, star, E prime. And here we have E minus E prime. This is a function of E. And this is a principal value integral. Okay, so that's, and then minus I over 2 W of E. And this is also a matrix 1, 2. So this W is when I take this integral. So, and I have here an integration over all channels and the summation over all channels. So I will get an imaginary part only if I am passing through 0 here. So it means that for every channel that is what we call open, so the channel that can have an open decay, I will get a contribution. The channel that is closed, that is below the threshold, I will get no contribution because I'm never going to pass through 0. So therefore, this W12, and of course, if you recall, this integration 1 over x plus I delta gives me pi times the delta function. So therefore, integration over energy disappears. So therefore, what I will get here is just W equals to 2 pi sum over all channels that are open. Integration over energies disappear, and I will have A C of this energy, which is the same as in argument here, times 1 times A energy for the state 2, complex conjugated. Okay, so this is an explicit form of my imaginary component W. Okay, and now this sort of concludes this part. Yes? Okay, so what I mean by open is coming back to our example. If I had my well, and I did perturbation theory for the state that is below 0, I never had an imaginary part. Because when I integrate over here. This is integration over my continuum. So 1 over E minus E of an integral is never 0 because this is below. So therefore, I never had an imaginary part in that integral. Right? This is called the closed channel. Now, if I have the state here, then this energy is above 0, and I am integrating above 0. So this difference passes through 0. Because various channels may have different thresholds. Right? So, again, referring to our example of two particles bound by a harmonic oscillator scattering off a wall. So if my kinetic energy is big enough, then I can start in the ground state, and once I hit the wall, my system can come out in the first excited state. So far away, I will measure my two particles in the first excited state, but moving slower, right? So that channel is open then. But maybe my initial kinetic energy was not enough. So if my initial kinetic energy is not enough, then I'm going to reflect back exactly in the ground state. Then that first excited state channel is closed because it's not allowed in the remote final state. So therefore, each channel has its own threshold. So, and my reaction, this energy, must be big enough for a certain threshold to be open. Okay? So, I mean, yeah, so, but again, I think that example that we discussed yesterday is a very nice example. So you take two particles bound in the harmonic oscillator. You take that system in the ground state, and you shoot it hitting a wall. So the system reflects back. And then the question is, the system can reflect back in the same channel that it came, which means the two particles would be in the ground state, moving backwards in the same velocity. Right? Remember the wall. I can erase this. So we had the wall, the system comes in the ground state. So this was n equals 0 harmonic oscillator. And then it reflects back. But if the energy is high enough, it can reflect back in slower, but with n equals 1. Right? So, but when is that boundary between 0 and 1? Of course, the boundary is exactly when you have enough energy to excite that state. So then that state becomes open. Okay, well, I can discuss with you separately later and trying to give you more examples of what means open and closed. Now, it's simply conservation of the energy. So if, yeah. Okay, so, but now coming back to this, if you're looking, so here we are looking more like on the structure concept. So these 1 and 2 are bound states. So, and in fact, you can think of this effective term, which is, I had my wave function in the P space, but then there was an interaction which takes me from P to Q. Then here I'm propagating in the Q space, because this is like a propagator, and then I'm coming back to my P space. So if you think of this diagrammatically, then this is a diagram. So you can look at it as a process where I had my state. So I'm starting here, maybe I can look at this with state 2. So I'm coming with state 2. Then this state 2 scatters somewhere with HPQ. Goes in the continuum, propagates in the continuum with this interaction 1 over E minus E prime, where E prime is the energy in the continuum. Then comes back with HQP into my P space, but state 1. So this is in some way the same diagram that we have discussed for the perturbation theory. Except now, because I'm using running energy, it becomes exact. Okay, so now this is about channels. Now the problem is not as simple, because I'll show you some examples more. It's not as simple because here I'm looking at the structure. So suppose I took a state somewhere, like in this picture, I took a state here. But this state now has two corrections. It has a Hermitian correction delta and this imaginary part W. So what may happen is that this delta may be enough to change position of the state, whether it's above the threshold or below the threshold. So I actually have to iteratively solve this equation, because this equation is itself a function of energy. And the energy determines whether this is open or closed. So the problem can be rather complicated if you're looking at all of these states. So you have to actually iteratively solve it. But if you're close to a threshold or above it, then this term W is usually small. All right. So then there is another important component that I would like to add here. Let me find it in my notes. So that I got this Hamiltonian, and then it would be nice to look also at the reaction part. So this is right now, I talk about the P space. And of course, in some way, Q space is completely symmetric. So what I can discuss is the reaction question. So how would I see what happens in the context of reaction? So this was a structure. So again, repeating, in order to solve the structure, I would take my Hamiltonian, effective Hamiltonian, I diagonalize it, I find its eigenvalues. The eigenvalues are complex, and I have to solve it iteratively as a function of energies. Then when I do it, what I will find is complex eigenvalues. Now, of course, then you immediately say, well, complex eigenvalues don't make sense. Well, they do make sense because we already know that these are resonances. So these are decaying states. But then, in order to see them, I have to do a reaction experiment. So in fact, just discussing these complex eigenvalues of this complex Hamiltonian will not tell me much. What will tell me is if I do reactions. So therefore, I need access to reactions. And then the reaction turns out to be can be done exactly in the same way. So if I think of Q space, then I will have a channel C coming in and then propagating inside of my system. And propagation inside of my system, so coming from C to state 1, here I will have a propagator inside of my system, which is E minus this effective Hamiltonian H E. And then I will go out to another channel, C prime, let's say. And in here, I'm propagating between state 1 and 2. So this will be a matrix element 1, 2. So this is how I would look at my reaction part. So therefore, I will have the exact same diagram, which this actually dictates me my T matrix, which is a transition between state C and C prime. So I will have C prime, which is a function of running energy. So here I will have amplitude A which is a function of energy, as coupling my state 1 with channel C. Then inside I will have my propagation, which is governed by E minus this H, which is also a function of E. And then I will go out in a channel A from a state 2, C function of E, and this can be C prime, right? Actually, it's drawn in reverse. C has to be that way, so it has to be C prime here. and this is the full summation over intrinsic propagation 1 and 2. So this is full summation between 1, 2. So it doesn't matter here. Right, so this is my diagram for my T matrix. So what happens is it's going to describe my reaction. And now this gives an interpretation to this effective Hamiltonian and to its imaginary part, because this is now an exact intrinsic propagation. Right, so it gives an exact propagator for inside of my nucleus. And this propagator can have an imaginary part. So, and this imaginary part gives me exactly the time-dependent evolution that we were discussing, these decays. All right, so another thing that I wanted to show you here is, I guess, this discussion about factorization. So this quantity is factorized, which is very important. So in principle, if you think of this A as a matrix, you can write this as 2 pi some A dagger. And if you do that, then we can consider the following question for scattering. So if I take this scattering process, and now I do it completely schematically. So I will have, let me call this part, this combined part, just for simplicity, H naught. So then what I have to look at here is the following. This important propagator that I have here is E. So let me write this, let me define G, which is just that quantity, 1 over E minus H. And this H of E, so this H of E is 1 over E minus H naught plus I over 2 W. Okay. So now if we look at this imaginary part as just correction, then I can say, well, G naught, this is by definition, be 1 over E minus H naught, just by definition. So then I can relate these two with the so-called Dyson equation. Let me write it following way. If I take 1 over G naught and take it minus 1 over G, then obviously this one is E minus H naught, and this one is E minus H naught plus I over 2W. So therefore we'll get W, because everything else, these two cancel out, I have only that part. So therefore this is by definition is minus I over 2W. Okay, so now I will cross multiply this equation. I will multiply it by G naught from this side, and I will multiply it by G from this side. So therefore this term will just give me G. This term will give me this cancel, so it will give G naught. And the last one will equals to minus I over 2 G naught W times G. Okay, so I'm sure you've seen this equation before. It relates me this propagator. So it tells me that my full propagator, which is corrected with this imaginary part, is, so it's G naught minus I over 2 G naught W G. Okay, so it's nothing special. In fact, it's also related to Born series that we have discussed, except it's in the energy representation. So here I find my full answer, but I need my full answer on this side. So what it turns out that since my W is factorized, so W is 2 pi A dagger, where A is some block matrix out of channels, then I can write it as my full propagator equals to G naught minus pi G naught A dagger G. And so that's, and there is I, which I should not forget. Okay, so this is my equation, and having this factorized form means that I can actually iterate it. So if I start with G being G naught on the first step, then on the first step, let me just substitute it a few times. So I will get G equals G naught minus I pi G naught A dagger A dagger. And then I will substitute this G again, which is G naught minus I pi G naught A dagger G. Right, so when I open it, you will see that this is G equals G naught minus I pi G A dagger G naught minus I, so it's going to be plus I pi squared, let me put it this way, minus I pi squared, and then I have G naught A dagger G naught A dagger G. And then I can substitute it again and continue. But you may notice already one feature that what I will have inside, I will always generate these powers here. So I will generate these two many powers. Right? So I will simply repeat it if I introduce it next time. This will be G naught. So I have G naught A dagger, G naught A dagger, G naught. And then the next one will go to a higher power. So this becomes a series. Okay, so therefore I can separate this I pi, it has to be G naught here, I pi G naught on this side, and then A dagger G naught at the end. And I will get a series. So let me write the final answer. So this is G naught, and then minus I pi G naught A, and then I have here a repeated A G naught A. So this will be 1 over 1 plus I pi A dagger G naught A. Right, this is this sign, and then I will have A dagger G naught at the end. So this is a summation of the full series. So this series is just 1 plus I pi A dagger G naught A plus the same term squared plus cube and so on. Sorry, it's minus here. So it's with a minus I pi. And that's what I will have. Okay, so what it turns out that in this particular case, this equation is this Dyson equation, given the factorized form of this imaginary part, can be solved exactly. Okay, so, and then if I would like to find my scattering T matrix, I guess I can start from, so this is my T matrix that I want. So my T matrix will be found, therefore, from T matrix will be found from A dagger full propagator GA. So when I take this, I'm also going to introduce this. So the only difference is this in G naught. So therefore, what I will do is I will multiply this from both sides, from this side by A dagger and from this side by A. So what I will get, therefore, is my T matrix equal. This term is just my K. Then I will have minus I pi, and then I will have A dagger G naught A, so which is K again. Then I will have 1 over 1 plus I pi K, because this is again K. And at the end, when I multiply by A, I have A dagger G naught A, which is K again. Okay, so this is my presentation, so I can actually simplify it. So I can take under common denominator. So this is going to be, if I multiply 1 times K plus I pi K squared, and this is minus I pi K squared because there is another K, divided by 1 plus I pi K. So this cancels out, and I will get that this is K over 1 plus I pi K. Okay, so this is so far just in the channel matrix form. Okay, so and then finally we recall that, for example, our S matrix from the first lecture was a unit matrix, which was a delta function. So minus 2 pi T matrix, I times T matrix. So therefore, when I put this in, I will have 1 plus I. So this unit, I write 1 plus I pi over K, bringing on the common denominator, divided by 1 plus I pi K, this one, and then minus 2 pi I K. So what I will get here is that this is 1 minus I pi K divided by 1 plus I pi K. Okay, so now we brought it to something that we have seen before already. For example, with resonances, we saw that the S matrix, the numerator and denominator are complex conjugate of each other. So, and in here, remember, K involves G naught, which is fully Hermitian, right? So this is a combination of my delta and the original Hermitian Hamiltonian. So therefore, K is the Hermitian matrix. So what it shows, what I have derived you is an important result, that it shows that S matrix is unitary. And now you see the key element in this unitarity was that my imaginary part, W, has this form. It has this A dagger A form, which I could use to solve my iterative Dyson's equation. And that leads to unitarity. So there is this close connection between unitarity and the factorized form of the matrix. Okay, so should we stop for a second? All right, let's stop for a second. I'll give you some other examples later.